Hello everyone, today we are presenting our project, the Internet Topology Explorer. Our goal was to build a tool that not only traces the paths of packets across the internet, but also analyzes how different protocols such as TCP, UDP, and ICMP experience routing differently. Traditional tools like traceroute provide only a single perspective of the network path. However, they do not really reveal how routing behavior may vary depending on the protocol being used. Our system extends this idea by introducing multi-protocol probing combined with visualization. Our project had two main objectives. First is to design and implement a traceroute-like tool that supports multiple protocols and customizable parameters. Second, to build an interactive visualizer that transforms raw network data into meaningful insights. We followed a modular architecture in Python. The main script orchestrates the traceroute process. Packets.py handles packet creation using Scapy, and parser.py processes responses to identify hops and extract metadata. The results are stored in a structured JSON file, which is then used by the visualizer. The core idea of our system is multi-protocol probing. At each hop, we send UDP, TCP, and ICMP probes instead of just one protocol. This allows us to observe differences such as protocol filtering, variations in latency, and differences in routing behavior across transport layers. We also implemented several standard traceroute features. Users can customize TTL values, packet size, destination port, timeout, and the number of probe series per hop. We also support batch input through text or CSV files and include DNS resolution for readability. To enhance our data, we integrate a geolocation API to map IP addresses to real-world locations. Internal IP addresses are filtered out because they do not have global coordinates. All collected data, including IPs, host names, RTTs, and locations, are stored in JSON format. Our visualizer provides two main views. The first one is the geographic view plots nodes on a world map and connects them using polylines to show the physical path packets. The logical topology view focuses on network structure, where nodes represent routers and edges are color-coded by protocol and scaled based on RTT. Finally, we addressed challenges such as requiring root permissions for raw sockets, handling packet loss through timeouts, and filtering internal network addresses. We will now move on to the implementation details.
Now we will walk through the core implementation. In main.py, the traceroute logic is implemented using loop over TTL values. Each iteration represents one hop in the network. When TTL expires, the router sends back ICMP time exceeded message, which allows us to discover intermediate nodes. At each TTL, we send probes using UDP, TCP, and ICMP. This is a key improvement over traditional traceroute. By sending all three protocols at every hop, we can directly compare how each protocol behaves under the same network condition. We also allow multiple probe series per hop. This helps improve readability and allows us to compute average RTT and packet loss more accurately. For each probe, we measure round-trip time using high-resolution timer. If no response is received within the timeout, we record it as a failure. In packets.py, we use Scapy to construct packets manually. This gives us full control over packet headers. TCP probes use SYN packets, UDP probes sends datagrams and target port, and ICMP probes use echo requests. This design allows us to simulate realistic network traffic across different protocols. In parser.py, we process responses from the network. If the response is received, we extract the sender's IP address and attempt DNS resolution to get a host name. We also analyze ICMP message types to determine whether we reached an intermediate router or the final destination. For example, ICMP time exceeded indicates intermediate hop, while ICMP echo reply or port unreachable indicates that destination has been reached. We enrich data with geographic information using an external IPA. Private IP addresses are filtered out since they belong to internal networks and do not map to real-world locations. In generate_with.py, we transform the raw results into a graph structure consisting of nodes and links. Each node represents a router, and each link stores protocol and RTT information. Finally, visualizer.py integrates everything into interactive interface using Steamlit. It allows users to run traceroute, view results, and explore data through maps and graphs. It also computes additional metrics such as average RTT and packet loss for each hop.
Now we will demonstrate the system in action. First, we run the traceroute engine on multiple targets. The system sends UDP, TCP, and ICMP probes at each hop and prints results in real time. As you can see in the terminal, each hop displays responses for all three protocols along with their RTT values. This allows us to directly compare protocol performance. We also generate a raw output file. This file summarizes raw results in a traceroute-like format, showing each hop, their responding node, and RTT values. Missing responses are represented with an asterisk. Looking at the output, we can already observe interesting behavior. In later hops, UDP probes frequently time out while ICMP continues to receive responses. This suggests that some routers or firewalls filter or deprioritize UDP traffic. We also notice that RTT values vary between protocols at the same hop. This indicates that packets may be processed differently depending on their protocol, possibly due to routing policies or congestion control mechanisms. Next, we examine the JSON data. Each destination contains a list of hops, and each hop contains multiple probe results. This structure preserves protocol-level differences instead of averaging them into a single value, allowing for deeper analysis. Now we launch the visualizer. In the geographic view, we see the path of packets plotted on a global map. Each node represents a router, and lines show the path taken by the packets. By hovering over the nodes, we can see detailed metrics such as RTT, average latency, and packet loss. This makes it easy to identify long-distance hops where latency increases significantly, such as transitions between regions or continents. In the logical topology view, we focus on the structure of the network. Nodes represent routers, and edges represent connections between them. Each are color-coded by protocol and scaled based on RTT. Thinner edges indicate higher latency, while thicker edges represent faster connections. This allows us to quickly identify performance bottlenecks. Finally, in the data view, we see a structured summary of each hop, including average RTT and packet loss. Users can also download the results for their analysis. Overall, the demo shows how our system provides both low-level data and high-level insights.
From our experiments, we observed that internet routing is not protocol dependent. Some routers respond to ICMP but ignore UDP or TCP probes, and latency can vary across protocols at the same hop. These differences highlight how network policies such as firewalls and traffic prioritization influence routing behavior. Our Internet Topology Explorer makes these differences visible by combining multi-protocol probing with interactive visualization. In conclusion, our system extends traditional traceroute by providing deeper insight into how the internet routes traffic and how different protocols are treated. Thank you for your attention.